for being here, and I'd like especially to thank Jarek for inviting me to give this talk. It's my pleasure to be with you, or let's say, although virtually. So it will be a great opportunity for, let's say, scientific exchange. And I'll be presenting, in fact, a work I did with Jarek himself about the ultimate origins of objectivity in physics, and he is one of the experts in this respect, let's say. So a few words about me. I'm assistant professor of mathematical
Carlo, sorry,
physics.
just so you know, you are not sharing screen yet, right?
No, I'm not. No,
okay,
exactly.
cool.
I'll start doing so soon. So yeah. So let me put in full screen mode. Right. So I'm assistant professor of mathematical physics at the University of Calgary. I've just started my new position, let's say 2 months ago. In the math department and the Institute of Quantum Science and Technology. And so as I just briefly summarized, today I'm going to talk about the universal structure of objective states in physics, in particular in physics that obeys the causality principle, which we believe to be something fundamental. And the tool I'm going to use for this purpose is the tool of general probabilistic theories. Some of you may be familiar, but some of you may be less familiar or maybe new to this area. But in any case, I'll give you a sort of gentle introduction to the subject, let's say, at the beginning of this talk. So without further ado, let's start, and I'll introduce the problem we're trying to solve. And as I said, this is a joint work I did with Jarek from there. Then there is Roberto Salazar, who now is a postdoc in Krakow, and then Paweł Hordecki. And so the basic problem we're trying to solve is the following. We know that classical theory is objective in the sense that if there are different people describing the same phenomenon, they in general agree on what happens during that phenomenon, or maybe in talking more about quantum state, they agree on the description of the quantum states, but of a classical state. But on the other hand, in quantum theory, since measurements are disturbing, then clearly whenever I observe something, I'm also changing the system itself. Therefore, the problem is that objectivity there is a much more delicate phenomenon. So in other words, different observers in principle can have different descriptions of reality. So now the problem is that, as you can appreciate, there is a tension between the objective behavior of our everyday experience and the fundamental reality of the world being described by quantum theory, where essentially the notion of objectivity seems threatened, let's say, by the act of observation. So now the question is, how do we explain the fact that we observe objective and classical behavior in our everyday world? Well, several proposals have been put forward. The basic one involves decoherence. So something is decohered, but still doesn't really account for objectivity, because objectivity is something more than decoherence. So decoherence just tells us that the world becomes classical. And then there is an upgraded version of decoherence called quantum Darwinism, where essentially there is survival of the fittest. So this is decoherence. So only the classical states survive to decoherence. And then also reproduction of them, in which case essentially classical states reproduce, they get cloned, they get broadcast to the environment, let's say. So this is quantum Darwinism. And then there is a final approach which was put forward by the group in Gdańsk, and Jarek was one of them. And at the time he was in Gdańsk, I think, which is called the spectrum broadcast structure. And I'll talk later about what I mean by this. So essentially, the origin of objectivity should be traced to the existence of a particular type of states called spectrum broadcast states. So SBS stands so either for spectrum broadcast structure or for, let's say, spectrum broadcast states. So now the main question is, from a foundational point of view, is what part of quantum theory is responsible for the origin of classicality and this objective behavior? So since we observe it from out of the quantum world, then there must be a way to understand how this happens. So now, how are we going to approach this problem? Well, two things. In order to understand what aspect of quantum theory is really responsible for this, we should look at quantum theory from the outside. So in other words, let's move out of quantum theory and let's consider also more general alternatives to quantum theory. And on the one hand, this will provide an answer of which part is ultimately responsible for classicality and objectivity. And the second part will also allow us to get, let's say, to understand what happens when we consider extensions of quantum theory. Because, you know, in the theory of quantum gravity, people start to consider extensions of the quantum formulae that reduce to the quantum one in the limit of let's say, low energy. Okay, so to this end, we use, as I said, general probabilistic theories. So general probabilistic theories are a framework that can describe all possible physical theories admitting probabilistic processes. So the basic instance of something that occurs in physics is something that occurs in a laboratory. So we want to be able to make observations and experiments in a laboratory in every possible physical theory. So we'll get something that we call a test. So the key thing is that here we don't want to give a very precise mathematical description of what a test is, in the sense that maybe a test is a quantum instrument in a quantum case. But in this setting, we just say that a test can be, in this, let's say, performed in a laboratory and will result in different outcomes, which are labeled by I. So these outcomes are classical. That's the key thing. And essentially, we can associate a different transformation, different operation occurring on the system for every choice of outcome. Let's say for every outcome we observed, we know that a particular transformation occurred in the system. So again, we're not saying what this transformation looks like in terms of mathematical description, although it will turn out that this, the most general mathematical description in which this thing can be, let's say, inserted and fit in is the notion of a symmetric monoidal category. So it's a very sort of abstract and sophisticated mathematical framework that allows us to obtain some results of regarding the structure of physical theories without knowing what the physical theory looks like. That's the key thing. So again, coming back to our experiment, if we have only one possible outcome, then essentially we can say that the test is deterministic, and in which case we call it a channel. So in other words, I know what happens in that particular experiment. Anyway, I just want to point out as a side remark, as some sort of food for thought, that, you know, determinism is often conflated with the notion of having probabilities, but you can see directly from here that this notion of determinism doesn't employ probabilities at all. So it's just the fact that experiments can result in possible different outcomes. And from this point of view, probabilities are just a quantification of how, let's say, uncertain we are about a particular outcome. That's
Sorry, Carlo, can I ask like two questions? So first, just about what you just said. So just on the terminology side. So if in the quantum theory I have just, let's say, a projective measurement, right? And I can have different outcomes with different probabilities. Would you call it a channel in your language or not? Because I'm confused.
No, I won't, because there are various outcomes. Because the idea is...
So basically, something that you call a channel doesn't reduce to something which is called a channel in the quantum setting.
yeah, what I call a channel reduces to a quantum channel, let's say.
Why? No. Like quantum measurement is a channel, right? Quantum measurement.
I would call it it's a quantum instrument rather than a quantum channel.
Well, okay, so I mean like P of M. Okay, so a P of M. Okay, just to be on the, because I'm very interested in what you have to say, but I don't want to get lost in terminology.
Sure.
Okay, so you have those so-called, let's say, quantum classical channels, right? I mean, there are channels that exist in quantum theory. I mean, for example, every P of M can give you a channel, right? So you map, basically you map your quantum state to classical states that have on the diagonal just probabilities of different outcomes. It's a legit channel in quantum theory. So somehow this thing you won't call a channel in your
no, exactly. I won't call it a channel.
Okay.
There are two reasons why, essentially, because this formalism roughly works with the idea that all systems, here denoted by A and B, are of the same type. So there is no sort of distinction between classical versus quantum systems. If we want to have that, then we need a much more structure, let's say, somehow. First of all. The second thing is that even when you consider a quantum to classical channel, what you get is somehow to say, a global, I would call it like the global representation of the P of M, in the sense that you get a description of all possible outcomes that occur. But now instead with this idea, I want to be able to focus on a particular one. So in other words, if I take your P of M channel plus the ability to read the outcome of the P of M channel, the specific outcome that occurred, then the thing stops being a channel.
I see. Okay, and then can you give, in quantum theory, just an example of so like a unitary, I imagine that like a unitary channel would be a proper channel for you. Also okay, so what you basically don't want to change the domain, like, so any just CP trace preserving completely positive map would be also in that sense a channel.
Exactly, yes.
Cool.
Yes, everything that is CP but not completely positive in quantum theory, I don't call it a channel. Sorry, that's CP but not trace preserving, I won't call it a channel.
Okay, thanks. I have some questions, but I ask them later.
Okay,
thanks.
Sure. Then we can also view a state as a particular type of action we do, which is associated with the preparation of a system. And in this case, we have no input. And indeed, you see from the diagram I wrote down that there is no input input wire, right? And dually, we have some tests that destroy the system in the sense that the system doesn't exist anymore. This is, for example, the case of quantum to classical channel, because the quantum system, if you wish, doesn't exist anymore after that. Just to connect with the previous question. So this is what we call measurements, and we represent this fact by the idea that there is no output, so no quantum system, or in this case, no generic system as output, but we only have a classical output corresponding to the outcome of the measurement. And in this case, the measurements are a collection of effects, and in quantum theory, effects are essentially P of M elements. Again, I use braces here in the graphical representation to mean that there is a collection of them, because each of them, let's say, represent what happens with a particular outcome. Again, but you see there are these labels that are sort of the classical outcome we observe. So now with this in place, we can build circuits. With these circuits, essentially can be both viewed as a sort of how these mathematical operations corresponding to these physical operations are composed together, but we can also view it as some sort of idealized rule to build an experiment. So in this case, what happens, I prepare the state rho I, which is shared between Alice and Bob, and then Alice and Bob do each some experiment getting outcome J and BM, so J and M, and then Alice does another measurement obtaining outcome K, and then eventually they both destroy their own systems obtaining outcome L and N. So whenever I have a system that has no external wires, like this one, because you see on the left there is no incoming wire, on the right there is no outgoing wire, this is associated with the joint probability of everything that is represented in the circuit occurring. And you see, this is how we bring in the probabilistic part. So in other words, we associate it with the idea of preparing and then destroying a system, and then what we get out of it is a probability. So now the probability is important because it gives us the linear structure of a theory. So every theory will be, we can associate a real vector space on with that theory. And say, well, it's real, that's so strange because we are used to complex vector spaces in quantum theory. So is that crazy? No, because also in quantum theory, we have a real vector space, and that's the real vector space of density matrices. Because again, being Hermitian, this is a real vector space, not a complex one. Although the entries of matrices are complex, but let's say linear combinations must be done with real coefficients. So, and the other thing is that since it's real, it can also be ordered in the sense that if I can consider, for example, coefficients of linear combinations that are all non-negative. If I do that, I obtain what they are called a conical combination, and in which case I'm able to talk about convex cones. It's not super important for this talk, although we use them quite a bit in the paper we wrote. But the key thing is that the idea that we have a linear structure, so we can have sums, and we can represent the physical operation of coarse graining through sums. So what is coarse graining? Coarse graining means going from a more refined description to a more, again, to a coarser description of what's going on. The example is, for example, if I roll a die, for example, the outcome is one is somehow an atomic event because you cannot decompose it further. But if I ask instead the probability of the outcome being odd, then this is not atomic because this can be viewed as the coarse graining of some outcomes corresponding to odd numbers in the roll of a die. Right. So this allows us to define purity. So something we call pure if it cannot be written as a non-trivial sum or coarse graining of transformations. So if I'm not able to decompose it further, then it's pure. So that's the general definition of purity in these general theories. Okay. So essentially, this is the whole physical treatment.
I ask still something here.
Yes.
Do you? Because I mean, also in quantum mechanics, but I guess in the context of GPTs, there is this possibility to take like convex combinations of objects.
Mm-hmm.
So
yes.
Here, do you just take this coarse graining into account when you define cleanness, or you implicitly also talk about have in mind this convex structure, which is related to those cones?
Yes. So I can tell you that in general, yes, we can introduce convex combinations, but this definition of purity works in more general case. The reason why I'm saying so, because convex combinations are typically associated with the fact that states are normalized. So in the case of quantum theory, that the trace is equal to 1. And therefore, if you sum two states that have a trace equal to 1, in general, the trace is not equal to 1. It will be, I don't know, 2, for example. But instead, if you rescale them with with some coefficients that form a convex combination, then the normalization is preserved. So the fact that there is a normalization of states to be preserved is a feature of a particular class of theories that are called causal theories, because in general this is not the case. So when the theory is not causal, and an example of this is the theory of quantum supermaps, it's not a causal one, then the notion of convex combination is too restrictive. let's say it can still be done, but it's too restricted. It doesn't capture the full idea of purity. You can have a glance of what happens even in the theory of in quantum theory. So a transformation here doesn't mean just a state, means everything essentially. So from that, everything that is physical and completely positive. So essentially, completely positive and trace no increasing is what we call a transformation in the case of quantum theory. So purity, according to this definition, is not being extreme in the sense of convex combination, but purity is associated with, in this case, with having only one Krauss operator. So a channel is pure in this setting, in the quantum case, if and only if it has just one Krauss operator. So, which means like being an isometry. On the other, so because there is another, let's say, approach, which in this case is too restrictive, where it requires, for example, channels to be pure, only those that are extreme, so that cannot be written as convex combinations of other things. But here, since we relax the idea of convex combination, we allow also, we want to exclude that the channel can be written as a sum of something that is trace decreasing, let's say, strictly trace no increasing, actually, to be more precise. We want to allow also for that case to rule out that case as well. That's essentially the reason.
Thanks.
Okay, so I mentioned the causality, and indeed that's what we are going to talk about. Our work focuses on causal theories. What is causality? Causality is the idea that information cannot backflow from the future. So in other words, the probabilities of an experiment occurring now is independent of what I decide to do later on to the system. So future doesn't influence the past, in other words. Unfortunately, this is the case for the theory of quantum supermaps, but for, let's say, quantum theory, this is definitely not the case. For classical theory, this is not the case. The key idea is that causality forbids signaling. So if the theory is causal, states are automatically non-signaling if they are bipartite, shared between Alice and Bob. They cannot use these states to do signaling because they would violate causality. So essentially, causality is a requirement that information cannot travel faster than light. The key thing for our work is that this property, which essentially, since information goes from the past to the future and not vice versa, then I can decide what to do in the future based on what I did in the past. So what we call a conditioning, essentially. And we can, in this specific example, we can perform a test according to the outcome of a previous one. Specifically, what I can do here is that I first make a measurement, and if I obtain the outcome AI, I prepare state rho I. So again, the preparation of rho I is conditioned on first obtaining outcome I in a suitable measurement. So we're going to use these tests quite a bit in this result, in this, let's say, talk even, and therefore it's good to give them a name. It's called measure and prepare, because first you measure and then prepare. And the key thing is that the existence of such tests is guaranteed by causality. So whenever a theory is causal, these things exist. Okay, so now let's move to the meat of what we discussed. So essentially the talk addresses two areas. The first is the coherence. The second one is the issue of objectivity. And the last part, we also talk about a strange problem, which is a locality problem for classical theory. So it's very strange, right? Because we are not used to thinking of locality problems related to the emergence of classical theory. But in fact, in general, we should also worry about those. So again, the emergence of classical theory can also be non-local, which is very strange. Anyway, so let's start with this. So the key idea is first to give a precise definition of what we mean by classical theory. I should say that in this work, for the sake of simplicity, we limit ourselves to the case of finite dimensional systems. And in this case, therefore, the version of classical theory we're going to use is based on finite classical theory. So it's the theory of probability distributions over a finite set. And geometrically, the set of states, which are probability distributions over a finite set, is a simplex. So here you can see a few examples of simplices let's say, low dimension. The key property of classical states is that there is a measurement that jointly perfectly distinguishes them. So in other words, if I don't know which of the states I prepared, this measurement is able to tell me with certainty which state I prepared. So it's so the key property is, again, perfect distinguishability of states. And another interesting thing is more technical, but it will play a role shorter, is that if I take the set of effects, the set that, let's say, effects span by conical combination. So if I just take effects and take linear combination with no negative coefficients, I obtain what is called the cone of effects. And in this case, the cone of effects is the dual cone of the cone of states. So if I do the same trick with states, if I take conical combination of states and I get the cone of states, then the cone of effects and the cone of states are dual to each other. That's essentially what happens in classical theory. It also happens in quantum theory, but here we are interested in a classical case, because I'll shortly show a case that where essentially if I restrict the cone of effects to be not the dual cone, but something smaller, then I obtain something crazy going on. Okay. So the first step is to identify the classical subtheory of a theory, because this will be the target of my decoherence process. So we know that classical systems are present implicitly because classical outcomes are, the outcomes of experiment are classical. But now we want to introduce them explicitly. So we want to look at them as emergent, in other words. So what is this? So what are they? Again, we want to find the maximal sets of perfectly distinguishable pure states. So pure states, remember that in classical theory, are perfectly distinguishable. And if suppose I find two states that are two pure states that are perfectly distinguishable, I want to find whether I want to see whether I can find other states, other pure states, such that if I add them to the original states, I'm still able to jointly distinguish these states perfectly. So that's why I want to find maximal sets. So the largest set of states, pure states, that can be jointly distinguished. Now the question is, this is what I want to find, but can I find it? The answer is no. And for the first time, we give an actually conclusive answer to this question in this work. And the crazy thing is that in order to find a theory that has no classical states, we start, in fact, from classical theory itself. We start from the classical treat, here represented with this simplex. And instead of allowing all possible effects, so here what you see in the second triangle is actually a slice of the cone of effects. Imagine that you're just sectioning the cone. And you get, since it's dual, essentially it has the same shape as the state space, basically. But now what I do is that instead of allowing all the orange triangle, I restrict myself. So I just take the smaller blue triangle like this. So just take, instead of taking all extreme effects, I take let's say convex combinations of extreme effects with equal weights, so weight 1/2. So now the question is, if I reduce the number of effects, then there's the risk that I'm not able to distinguish different states anymore. Distinguish I mean by tomographically distinguish different states. So suppose that I only have one effect in my theory, then clearly all states give the same probability. So I cannot do any tomography, any interesting tomography there, because everything reduces the same thing. So now we have to wonder whether such a restriction disrupts the shape of the state space. And it turns out that it doesn't. Nevertheless, because again, the state space still looks like a classical theory, but with this restriction, the effect is that we lose the perfect distinguishability of pure states. So the pure states that you see in this sort of fake classical theory, which we call the restricted treat, are no longer perfectly distinguishable, despite the state space looking classical. And even if we compose systems, so even if we take like tensor products in suitable sense of these things with a larger number of copies, these things don't get distinguishable. That's a really remarkable feature of this. So there is no way that this thing, let's say, that the theory starts having, let's say, distinguishable states, perfectly distinguishable states. Okay. So now, therefore, first of all, we need to focus on those causal theories that allow classical
Carlo,
states.
may I have a question? Because I might have got lost a little bit because I thought that when you were talking about distinguishability, I was like thinking about, you know, single shot discrimination, and yes. You changed to tomographic, and I didn't manage to.
Oh, yes.
So could you just like click quickly?
Yes. So here we are mostly concerned with what we understood correctly, which is the single shot distinguishability of states. I only talked about tomographic distinguishability for the problem that we restricted the set of effects. So if we have a smaller set of effects, we can lose tomographic power. So saying that let's say the original states I wrote down of the triangle are actually the states of the theory is unjustified unless I prove that even with that restriction, the state space remains the same.
Mm-hmm. Okay.
Because with that restriction, I can lose so much tomographic power in principle that maybe all states become indistinguishable. They only have one state.
That's right, sure. So the point is that even though you like have still the tomographic power in this restriction, you
exactly
don't have any more like single shot.
Exactly. So tomographic power is preserved. So the restriction preserves tomographic power, but on the other hand, it doesn't preserve the single shot distinguishability of states.
Okay, super.
That's basically what happens. Okay, so first, this counterexample shows that in general, finding classical subtheories of a theory is actually non-trivial. So we have to focus on theories that admit those, in other words. So what do I do? So suppose I find two states that are perfectly distinguishable, two pure states. Then what I do is that I try to enlarge this set in order to take the maximum number of pure states that are still jointly perfectly distinguishable. And I say that the convex hull of these pure states that are perfectly distinguishable will be my classical subtheory, which in this case is denoted by this bold alpha. So which sometimes we call it also the classical set. Now, so remember that the previous counterexample shows that even if the state space looks classical, like in this case, like in this convex hull of perfectly distinguishable pure states, we need also to check whether effects work like in classical theory, because they may have some crazy restrictions by which essentially the theory is non-classical, like in the previous case. So how do I find the effect of such a theory? I take the original, such as classical subtheory, I take the original effects and I restrict them to alpha. So what do I mean by this? So I just let these effects, let's say, occur on alpha, and basically I identify effects that give the same probabilities on all classical states. So more formally, what I do, I introduce an equivalence relation. So I say that two effects are equivalent if they give the same probability on all possible states in this classical subtheory. And I identify such effects. Well, so the set of these equivalence classes, so essentially these identified effects, what are these identified effects? They are essentially, we can show that these effects are generated by means of, let's say, conical combinations from the effects that distinguish the state. So in other words, again, this operation of restriction of effects gives me essentially also a classical subtheory in terms of effects, not just in terms of states. Okay, so now that we have classical subtheories, we are ready to understand whether a decoherence exists and what its properties are.
Sorry, Carlo. One question. So I'm thinking on this like classical limit of quantum theory. Mm-hmm. So there, the way I understand, it's not always the case that you get this objectivity or like, okay, you get this classicality on the, like for, you don't always look like, you don't always take the maximal classical subtheories. So like when you have like a system of many spins, right? So it may happen that for, let's say that only when you do some coarse graining, you have some classical description, right? If you know what I mean, right? So why to choose those maximal classical subtheories? I'm not sure if I.
No, I understand your point. Yes.
So I mean, think of like a classical oscillator, right? It has infinite number of distinguishable states, but in practice, that classicality is somehow realized on a bit different level. Yeah.
Yes, yeah, I know. This is a question I already received because people say, well, for example, coherent states are those that are classical. In other words, let's say that, yeah, we can argue on different definitions of classicality. Let's say that this is sort of a standard one in people doing, let's say, sort of hardcore quantum information theory, that essentially the signature of classicality is the distinguishability of states. As you also noticed, you previously said that, for example, P of M is a quantum to classical channel. And how do we represent the classical part? We represent it by means of a fixed orthonormal basis, and being orthonormal being distinguishable. That's the idea, essentially, from that point of view. Now, so this is regarding the distinguishability part. Regarding instead the maximality, so here I should say two things. First of all, that the idea of considering, no, I should start from the second thing I wanted to say, in fact. So a theory, so in quantum theory, it turns out that for every system, there is a very well-known notion of what I mean by a maximal set of classical, maximal set of distinguishable pure states, because it's just an orthonormal basis, and all orthonormal bases have the same number of elements, which is the dimension of the Hilbert space. Now, I can think of a theory in general where the number of, let's say, where different maximal sets have different numbers of elements, because they are not based on vector spaces, like on Hilbert spaces, like in this case. So maximality is not related to taking the largest of these maximal sets, the larger in size. No, it's not like this. This is what I don't mean this by maximality, by taking the largest of those. What I mean by maximality is that if I pick two states that I know to be perfectly distinguishable, I can still try to keep other pure states to see whether I can still preserve the property of being jointly distinguishable in a single shot. And then I take the maximum number of pure states I can add in such a way that jointly they are perfectly distinguishable. So it's maximal in this sense, let's say. This is what I mean, indeed. So now you say, well, why do we need to do this? Well, essentially because in quantum theory, again, if a system is d-dimensional and we want to study the coherence will be on a d-dimensional classical system. It won't be like, I'd say in most cases, people are not interested in studying the coherence from a d-dimensional system to the single bit, let's say. But they wanted somehow to preserve the dimensionality of the system. So that's why I require this property here.
Thanks. Yeah, I'm sorry for disturbing you.
No, that's fine. They're very legit questions and very interesting as well. Okay, so again, we want to look for the coherence. So when we identify a classical subtheory, we want to map essentially all original states to that. So what are the features of that decoherence in general? First of all, the emergence of classicality isn't a probabilistic fact. Otherwise, we wouldn't see classicality in as a stable theory. We would only see it probabilistically. So these forces us to consider only deterministic transitions to classicality, so in other words, channels, then clearly if a state is already classical and I decohere it, nothing happens. But everything else becomes classical. So what is then a complete decoherence? So if I have a classical set alpha, a complete decoherence to alpha is a channel that has the following two properties. It leaves classical states invariant, as we just said, because they're already classical. And it maps every state to a classical state. So very simple definition. It turns out that, in fact, this definition is so weak and general that something strange can happen. And then we'll see. So what are the properties? So if I apply the decoherence twice on a given state, then it's like applying it once, because once the state is decoherent, it becomes classical. If I apply it again, the decoherence, nothing happens. So it's very interesting. Now, this is just a more a side remark, that saying that the action of decoherence applied to every state is the same as applying twice as applying once is weaker than saying that actually the decoherence squared is equal to the decoherence. So composing decoherence twice, I get the original decoherence. Because in order to have this property, we need something called local tomography. Local tomography is essentially the ability of doing tomography on bipartite state using product measurements. We can do this in quantum theory, but we cannot do, for example, in real quantum theory, in quantum theory with real numbers, so where no complex numbers are allowed. And actually, I wrote a paper recently with Alex Streltsov, who is also here in Warsaw, where we actually show a concrete example of two states that are orthogonal and therefore perfectly distinguishable in quantum theory, but then that are real. But then if we remove the access to complex numbers, these states become completely indistinguishable. So it's a really remarkable property to consider, let's say. Now, what are the other aspects of decoherence? Again, remember that I defined classical effects as the restriction of quantum effects to the classical subtheory modulo indistinguishability, modulo tomographic indistinguishability, essentially. Now I can also take an effect and decohere it using the decoherence. So it turns out that the original set, the one taken by identifying effects that are the same on classical states, is the same as the set of decoherent effect. However, while the decoherence doesn't change classical state, it may in principle change classical effects. So what happens is that there is an asymmetry between the behavior on classical states and the behavior on classical effects. So the behavior on classical states and the behavior on classical effects. Yes, that's strange, right? Because it treats states and effects in a different way. So
can I ask some funny question, like a mathematical one? So can you can actually imagine to have to define this map in a bit different way, just imposing that it doesn't change the effects, leaves the states classical space invariant, and then what happens? Can you have some?
Yes, I'll answer this question soon, because I'll show an example of a theory of a decoherence that we are always guaranteed to exist, that instead is symmetric on both, let's say.
Okay.
Okay, so, and that's basically the next slide. The question is, okay, we define what a decoherence is. The next question is, does a decoherence exist in all causal theories with classical states? The answer is yes. And how do I do this? Well, I take those perfectly distinguishable pure states, alpha i's, and then I take the measurement that distinguishes them, which is AI, and I construct a measure and prepare test. So if I obtain outcome I prepare alpha I, right? This exists in causal theories because of causality. again. So I know this. Then what I can do, I can take a full coarse graining of this. So I sum over all the outcomes like this. And what I obtain is that I get a complete decoherence. So this new channel here can be proved to be a complete decoherence. And we call it the measurement induced decoherence because it's induced by the action of measurement. Actually, yeah, I think I forgot because we also changed the terminology to test induced decoherence because one referee complained about the terminology. But again, for some reason, I'm still affectionate to the old form, let's say. But because again, like in quantum theory, this is associated with the act of measurement, and you can see this has a sort of familiar structure, if you wish, like a sort of a cat and bra structure, and then we sum over that. So you see, it's an interesting parallel that all causal theories have the decoherence that is associated with measuring the system and forgetting the outcome, like in the quantum case. It always exists, and so it has the same form. And also have some nice properties. For example, now we can remove the presence of rho. So this thing is, this property is valid also when the theory is not locally tomographic. And also now the decoherence is symmetric in the sense that it treats states and effects in the same way. And this decoherence, we are always guaranteed to exist. Now the question is the decoherence unique or not? And here we have an example where in a specific theory, we have different types of classical sets. Some of those have a unique decoherence, and some others instead have a continuum of decoherence. So this theory is the theory of the square bit. So essentially where the state space is a square. Now a classical set can be taken to be, for example, the vertical side, like in this case. So this is represented in black on the left. And then each row gets mapped to the vertical side like this horizontally. So this is the action of the decoherence on row. So it basically gets mapped there. And we can prove that in this case, the decoherence is unique. So on the side alpha 1, alpha 2, if we fix that, there is only one decoherence occurring. And of course, this coincides with the measurement-induced decoherence because it's the only decoherence we know that always exists. On the other hand, we can also take the classical system to be given by the diagonal of the square. And in this case, we have a continuum of decoherence that are parameterized by a parameter t from 0 to 1/2. And here I represented only the two extreme cases for t equal to 0 and t equal to 1/2. And in between, essentially, you get all possible decoherence. So if t is equal to 0, I get decohered vertically. If t is equal to 1/2, I get decohered horizontally. And in between, I can decohere in all possible directions, essentially. So you see, in this case, it's very different from quantum theory. Fixing the classical set is definitely not enough to fix the decoherence. And we can have multiple of those again. And by the way, I should also mention that all these decoherence are of the measurement-induced type. So even restricting to measurement-induced type of decoherence, there are multiple of them in general. There's not just one. But there's another strange property, some other crazy things happening outside the quantum world. So in two papers that also studied, that did, let's say, an initial study of decoherence in GPTs, they required, as an explicit requirement for their definition of decoherence, that the decoherence shouldn't be purity increasing. So essentially, if something is decoherent to a pure state, it should be pure in the first. It should have been pure in the first place. So the original state should have been pure. So again, in other words, a mixed state cannot be decoherent to a pure state because then I increase the purity. But look at what happens. In general, this is not true because again, take the square and again, the classical set given by the vertical side. Now, if I take rho to be on the upper side, the side between alpha 1 and alpha 4, then rho in that case is mixed because it's not an extreme point of that state space. It's mixed, but by this decoherence, it gets mapped to alpha 1 because this decoherence projects essentially horizontally. So something that is in between alpha 1 and alpha 4 gets decohered to alpha 1. So a mixed state gets decohered to a pure state. So this is another token that, in fact, the notion of decoherence and of coherence and purity are really different, because I mean, too often people, especially like in talks for the general public, people say, well, what's the effect of decoherence? The effect of decoherence is the effect that basically we go from pure states to mixed states. And they show the classical picture that originally we have only of the histogram showing, and then they show that basically with decoherence, then I also have off diagonal terms and these things of that. So I say, oh, this is a mixed state. But in fact, there are two very distinct notions here. And in quantum theory, it's true that the decoherence is purity non-increasing, but in other theories, it's not. So essentially, purity and coherence should be kept very distinct as concepts. Okay, so after this part of decoherence, we go to the final part of my talk, which deals with the issue of objectivity. So what is objectivity? Well, objectivity is associated with the existence of objective states. And in the original definition by Olivier, Poulin, and Zurek, an objective state is something that many observers can find out, can determine without disturbing it, and they also agree on what they find. So this idea, which is just words, was put into a precise mathematical definition in this paper by Paweł Horodecki, Richard Horodecki, and also Jarek, where they show that essentially in quantum states, if we turn essentially this definition from words to, let's say, formulas, this basically picks out a particular type of states, which are called spectrum broadcast states, SBS states. What are these states like? Well, this is a quantum state, as you see. Then later on, I'll show you how it works in the other theories. So I have a system S, and in this system, I have an orthonormal basis J. So I have a convex combination of these the states of these orthonormal bases, and then they are tensored with the same index J, and tensor across different environments. So there are different fragments of the environment. The key thing is that for every environment, if I change J, the states, so if I change the label J from, let's say, 1 to 2 or whatever, what I get are orthogonal. So they have orthogonal support. So for every fixed environment, the states rho J, EL, and rho K, EL, let's say, are perfectly distinguishable. So here we extend the notion of objectivity from quantum theory to outside. So again, we start from the usual setting of quantum Darwinism, where we have a system and then we have several environments, one for each observer. Then there is an observer on the central system that acts as a referee and measures on some classical set alpha, right? And the idea is that the other players who only have access to their system let's say, sorry, to their environment fraction, they win in this game if they find out the state of S, the state that the referee essentially has prepared somehow, without disturbing the overall state. So what kind of notion do we use for non-disturbance? We use the so-called Bohr non-disturbance. And we say that a test is non-disturbing if it's non-disturbing on average, if you wish. So in other words, if I coarse grain over all possible outcomes of a test AI and I apply this to the state rho, I get the state rho back. So that's the notion of non-disturbance. Then, since again, we want to be able to repeat observations, we look for measurements that we call sharply repeatable. So a measurement is called sharply repeatable if, sorry, not a measurement, it's a test more precisely because it has an output. if essentially pi pj is delta ij pi. So this should look familiar because, for example, for normal measurements are tests of this type. And in fact, the original paper only focused on for normal measurements in terms of objectivity. But now, in fact, in quantum theory, these sharply repeatable tests are also more general than for normal measurements. Because, for example, we can take a quantum instrument where each quantum operation is given by, is of a measurement prepared form, where I measure on the project, let's say, on the support of a given state, of some given, states with orthogonal support, sigma j's, and then I prepare those states. So again, sigma j's have orthogonal support. Pj here in this expression is the projector on their support. And this can be easily proved to be a sharply repeatable test. But if sigma j is not a pure state, then this is not for normal measurement. So again, this notion of sharply repeatable tests generalizes that of for normal measurement, even in quantum theory. And in particular, we can always construct a sharply repeatable test in every causal theory. Indeed, if I find some states rho I that are perfectly distinguishable by some measurement EI, again, I use the same trick, which is guaranteed by causality, of doing a measure and prepare. So first I measure on EI and then I prepare rho I. And what I get is a sharply repeatable test. The key message is that these things exist in all causal theories thanks to causality. Well, with this in place, we still miss the last ingredient, which is the condition known as strong independence. So it's the fact that the only correlation between the players is the common information about the system. So essentially this is translated into the fact that if they make observations, different observers, and let's say they agree, and they agree, since they cannot have like joint correlation between different observers, then the state in the environment should factor out into the tensor product of the states in each fraction, in each fragment of the environment. So the proof of the theorem is very similar. I shouldn't say very similar because it uses different techniques from quantum theory, but let's say the idea behind it is similar. And we find out that we get that objective states in every causal theory exist, first of all, and they are all given. So it's a necessary and sufficient condition in more mathematical terms by SBS states, where we have a different definition right now because the alpha i's are pure states. So the pure states of a classical subtheory on the system. And in every environment fragment, I am considering perfectly distinguishable states, which might be mixed as well, but the key thing is that they are perfectly distinguishable. But the important message for this theorem is that, again, objective states in every causal theories with classical states are given by SBS states, and only SBS states are of this form. There are not any other possible types of objective states. So again, objectivity is associated with SBS states universally in physics, not just in quantum theory. Now the question is, why do we have that? Because maybe the idea of objectivity is so important in physics in order to be able to have a description of reality that this justifies its universality. So we observe it in every possible physical theory. It's not something very specific. Originally, we thought that it would be restricted to specific kinds of theory, and we were really surprised to find this a very general and universal result. Okay, so now the last couple of slides about my talk are on the issue of locality in the emergence of classical theory. So that sounds strange because we are not used to thinking about locality in this sense. So I must say that what I mean by locality is not the locality here, it's another type of locality, but still it's associated with the idea that something is non-local, in other words. So the idea is to study what happens when we have a bipartite system, and we want to study how classicality emerges on that bipartite system. So suppose we have a classical subtheory alpha for system A and a classical subtheory beta for system B. So it's Alice and Bob each have a different classical subtheory. So how do we combine them? So can we say that the classical subtheory on the joint system can be written in terms of the classical subtheories of each subsystems? So that's the question, roughly speaking. So if alpha and beta are sort of true classical systems in some sense, then we expect them to compose according to the rule of classical systems. So again, no entanglement, just you know, correlations, just separable states, if you wish. So again, if the theory is local, we expect that the classical subtheory for AB can be written in terms of the classical theories of A and B. And essentially what I do is that I take tensor products of alpha, a pure state alpha I with a pure state beta J on Bob's side. So alpha I is on Alice's side and beta J on Bob's side. Take those tensor products and then take the convex hull of these things. This is what I expect, right? And we also expect that the decoherence will factor out, as it was one of the requirements in this other paper about decoherence in GPT. So the decoherence on alpha on alpha beta, so on the composite classical system, is actually the tensor product of the two decoherences on alpha and on beta. So in other words, everything behaves locally in terms of the emergence of classicality. However, these things here are far from trivial. So they're not obvious at all. And I'll explain why they're not obvious. The first problem is that the product of two pure states may not be pure in a general theory. And there is a counterexample in this paper by Barnum, Graydon, and Wills, where they show that in quaternionic quantum mechanics, the product of two pure states is mixed in general. And what happens also is that the product of two pure maximal sets may not be maximal. So in other words, there are some non-local degrees of freedom in classicality. So AB has more classical states than just A and B taken alone, in other words. And there is an example of this property in a theory in this paper by Hardy and Wouters called local holism and and it's associated with real quantum theory, in other words. So in order to avoid these problems, we decide to impose two conditions. The first is that the product of two pure states is pure, in order to avoid that problem. And the other one is that the product of two pure maximal sets is still a pure maximal set. So again, they are pure and then they're also maximal. That's the key property. So why do I claim that without these axioms, there might be holistic behavior? Because if the product of states isn't pure, if I want to construct a classical state for AB, since I need to look for pure states in order to do so, for pure states on AB, if I cannot construct pure states of AB based on the pure states of A and the pure states on B. So I have to look for completely different states. So in other words, the behavior is extremely holistic because the classical subtheory for AB has nothing to do with the classical subtheory for A, and the classical subtheory of B is a completely different beast, completely different object. So again, I cannot reduce classicality in the composite system to classicality in the two subsystems. So that's why I say it's very holistic. Now, suppose instead we don't have problem one, but we have problem two. So we had the problem of information locality. So the product of two maximal sets pure maximal sets is not maximal. So in other words, when I construct a pure maximal set for AB, I can use some states of A and some states of B, some states in alpha and some states in beta, let's say, in order to construct it. But then this is not maximal, this is not enough. In order to have the full maximal set on AB, I need to pick other states of AB which cannot be reduced to the classical subtheories of alpha, of A, and the classical subtheory of B. So again, this theory has some degree of holism. So Therefore, these are the problems again. But now, even if we impose these two axioms in general, so in order to rule out this holistic behavior, we cannot say anything about the behavior of the decoherence. Again, because our definition of decoherence in general is so general that has very little properties. However, if we focus on the measurement-induced decoherence, then in the presence of the two axioms, then we can prove that the decoherence factorizes as a tensor product. So the decoherence on the composite classical system can be written as the decoherence on Alice's classical system, tensor product, the decoherence with on Bob's classical system. So again, this is another token suggesting that the measurement-induced decoherence is actually the most physically motivated one. Okay, so conclusions, finally. So again, first of all, we learned that not all causal theories admit classical subtheories. So a sort of suitable classical limit reachable by decoherence. That's the example of the restricted treat. But if they do admit a classical subtheory, there also exists a decoherence process on it. Again, this decoherence process is induced by the act of measuring, like in quantum theory. And the other important result is that objectivity exists in causal theories with classical states, and its ultimate reason is the fact that its ultimate origin comes from SBS states. So SBS states characterize objectivity in all fundamental theories. So now, if I ask what's the ultimate origin, so what's the part of quantum theory responsible for objectivity, I can say that's causality, and that's also the existence of classical states, and very little less. And actually, and objectivity takes place through SBS states. That's the key thing. So the ultimate origin, the ultimate reason for objectivity is actually causality. So it's nothing very peculiar to quantum theory at all. So this suggests going beyond quantum theory also for other paradigms, like for example, quantum Darwinism. So the whole machinery of quantum Darwinism, is it really quantum, or maybe it's also very general from that point of view. So maybe again, objectivity and classicality are necessary ingredient to do physics. Maybe. So we need to explore, I think, these directions and give an answer to these questions. So, and I think that this is a promising research area and very interesting for both people who are interested in quantum Darwinism to see its ultimate origin and also domain of applicability, but also for people studying GPT. Indeed, this is the first paper in the literature, the one we did together, where we showed a comprehensive account of the properties and issues related to decoherence in GPTs, which, I mean, there were kind of attempts, but they were only partial, and they didn't identify the right properties, and they also imposed some properties that were too restrictive, that go against the definition, the very definition of decoherence. Okay, so here are some references to the papers I mentioned, and that's essentially the end of my talk. And I'd like to thank you for your attention and also the questions you asked me during my presentation. Thanks very much.
Thank you.
Thank you very much, Carlo, for the talk. Now the questions, maybe. There were quite some questions during the talk, but
I have some questions.
Okay.
So I wanted to ask about this holistic behavior that you described on one of the last slides. So yes. If you could go back there. Right. Yeah. So this one. So can you okay, this is just some explain once again, why is this why we are so against it? Maybe I would phrase it like this. Philosophically, it is I would say, something like we like to think that we are kind of not the sum of particles in our bodies or something like that, right? And yes. So what is the exact motivation for throwing this away?
the exact motivation is essentially the fact that classical theory itself is not holistic. That's the reason, the ultimate reason. The idea is as follows. So think that, suppose that classicality is reached on A. So A at some point becomes completely classical system. Then also think that classicality is reached on B. So B at some point becomes a completely classical system. So what I have here is that I have two classical systems interacting with each other. So it's not, it would be very surprising that if I bring in two classical systems that when they put into interaction, then they stop behaving as classical systems, but suddenly there is some sort of activation process coming from the original theory, if you wish. So in other words, we can actually explain this in the following way. So saying that once we reach classicality, the system should forget completely about the previous story of the theory, the previous theory, in other words. So if A becomes classical and B becomes classical, when they compose, they should compose as classical systems. They shouldn't compose in a way that remembers that originally A and B were not classical, in other words.
Right. Okay, but this is like okay, I am like not really like acquainted with all of this stuff, but well, I mean, just on the high level, if you have some two even classical if you have some like, I don't know, classical states of even some quantum systems, then if you know, the quantum systems are kind of complicated, so if you put them together, they might interact in such a way that it stops being
but
classical,
if you take the how to say the definition I gave of a classical state, like being orthogonal pure states essentially, or convex combination of these things, but let's focus on the pure one. So orthogonal pure states. Now, and suppose I have A is a system with dimension D, and let's say dA, and B is a system with dimension dB, right? Then when if I compose these two classical systems, so these two orthonormal bases, I find an orthonormal basis which for the joint system AB. So in this case, quantum theory, despite being holistic, let's say, if you wish, as a theory, but when classicality is reached, then the whole disappears.
Right. Okay, I see. Yes. Good. Okay, thanks.
Okay, more questions? Michał.
I have one related question actually about this holisticity. So can one maybe reverse the question? And you know, in the context of GPT, people are like, there is this line of research where in which people try to single out, let's say, quantum and or classical theory out of the landscape of GPT, right? So can one maybe like, did you think, like, what if one let's say imposes those principles that you don't want to be holistic, right? Like from the perspective of the coherence and reaching classicality, are there some theories that are non-quantum and non-classical that satisfy those principles?
Yes, I'd say yes. Well, there is definitely, well, it's still similar to quantum, but like quantum theory in a real Hilbert space,
yeah, for me,
satisfies this. Yes, it's a variant. But for let's say, for example, if I take the square bit and I take two composites of those composites of this, then definitely. So in order to find a theory where the product of two pure states is impure, we have to find very contrived examples. It's not like something that comes naturally, let's say. So that thing is definitely satisfied if when we compose two squares, let's say. So when we get a pure box, and also the second one definitely is satisfied. So that's an example of theory. That's neither classical.
So pure like pure boxes, then sorry, like pure boxes would be a counterexample.
Yeah, exactly. That's
okay.
Yeah.
Thanks.
because again, even the counterexample they constructed where this information locality phase is also extremely complicated and contrived. So it's really, really weird.
Okay, any more questions? I don't see, so maybe if I may, I have one comment concerning your last slides and the question whether quantum Darwinism is really quantum or not. How I see the feelings is like that, but in fact, in this work, we are showing that quantum Darwinism is more general than just quantum theory. And why? Because it's not so clear from Zurek and collaborators' works that one has to distinguish the idea of quantum Darwinism from the proposed check for whether this quantum Darwinism happens or not. Mm-hmm. And the idea is like Carlo mentioned and somewhere during the presentation, that there is a propagation of redundant copies of the same information about the system, and these copies can be reliably, this information and records can be reliably read by independent actions of independent observers without disturbing neither the system about which we are trying to learn something, nor the observers among themselves. Okay, so that's maybe a complicated way to say that many observe the same without disturbance. So at least how I understand the work of Zurek and collaborators, I would say it's not so easy to read it from their works. I would make a distinction between the general idea, which can be called quantum Darwinism, so this not only that the fittest information about the system survives interaction with the environment, but also it manages to replicate in many copies in the environment. Mm-hmm. So that's the basic idea. And then comes, okay, the practical question, how to check whether it happened or not. And Zurek and collaborators, historically, they proposed a condition which is based on quantum mutual information, mm-hmm. Which is sometimes called quantum Darwinism, sometimes I also call it quantum Darwinism, but mm-hmm. sensu stricto, I would say that it is a condition, some sort of a witness, nonlinear witness, for checking whether quantum Darwinism happened or not. We had some reservations about the efficiency of this witnessing, mm-hmm. and propose another more direct way of checking, which is this SBS. Okay, so I would say that in a sense, this work where I must say Carlo was kind to mention me on this work, but mostly it was done by Carlo and Roberto. So in a sense, this work does show that quantum Darwinism is something more deeper than just quantum. Mm-hmm. Yeah, because we show that a particular witness of quantum Darwinism in the sense of SBS states, they appear in the theories where we have causality, causality and classical states. Okay, of course, the original Darwinism condition of Zurek, the one with mutual information, it's in general impossible to move beyond quantum just because you don't know how to define mutual information.
Yeah, there are some ideas, but they are kind of, I mean, yeah. there is not a unique way of defining that quantity, let's say so.
Yeah, so in a sense, I would say this work shows that this Darwinism idea is more general, but we show it not via original witness for Darwinism of Zurek and collaborators in the team, but we show it via these SBS states.
Mm-hmm. Right. Yes, exactly. Yeah, thanks for your comments.
My pleasure. Are there any more comments or remarks, questions to Carlo? Well, if not, then I think we can thank Carlo again for the very nice talk.
Thank you.